Hi everyone. This is joint work with Yossi Arjevani, Yair Carmon, John Duchi, Dylan Foster, and Karthik Sridharan. Given a smooth, potentially non-convex function f, the goal of our work is to find an epsilon stationary point of f, that is a point x hat, such that the norm of the gradient of f at x hat is smaller than epsilon. We operate in the setting where we can access information about the function through stochastic pth order queries. Specifically, on every iteration at a point x, the optimization algorithm observes unbiased estimates of the derivatives of the function f up to the pth order. That is, when p is equal to 1, on every query the algorithm gets a stochastic gradient. When p is equal to 2, the algorithm gets a stochastic gradient and a stochastic Hessian. And correspondingly for higher p, the algorithm gets a gradient, the Hessian, and the derivatives up to the pth order. A motivating example of this is the machine learning setting, where x corresponds to a set of models and f corresponds to the unknown test loss. For many such problems, even though f is non-convex, finding epsilon stationary points suffices to minimize the test loss, and one can easily query stochastic pth order derivatives using the dataset in hand. More formally, in the pth order stochastic optimization setting, we assume that the returned estimates are unbiased and have bounded variance under the respective operator norm for all order up to p. Further, we also assume that the objective function f is well behaved and has Lipschitz derivatives up to the pth order, and that the initial point x naught has suboptimality bounded by delta. Under this setting, the question we are interested in is how many such pth order queries are required to find an epsilon stationary point of the underlying objective. Let us start by the deterministic setting. Here we have a complete picture. We have matching upper and lower bounds for all values of p. The specific rates are given on the left, and the trend is presented in the right plot. Specifically, the more higher order information we get, the better the rates are, as one would expect. Let us now see what is known in the stochastic setting. When p is equal to 1, that is in the first order stochastic optimization, SGD achieves the rate of 1 by epsilon to the 4. This rate was recently shown to be optimal for first order methods by Arjevani et al. The same rate can also be obtained by an alternate algorithm. That is, pick up the corresponding first order algorithm in the deterministic setting, but instead of using the exact gradient, draw sigma square by epsilon square queries on every iteration and use the empirical estimate of the return stochastic gradients with the deterministic algorithm. Such a strategy can also be used in the higher order setting as well. That is, run the corresponding deterministic algorithm with empirical average of sigma square by epsilon square fresh draws on every iteration. This suggests that the stochastic rate is at most deterministic rate times sigma square by epsilon square. Furthermore, given the optimality of this approach for p is equal to 1, one may be tempted to conjecture that, in fact, for higher order setting, that is p larger than 1, the stochastic complexity is exactly equal to deterministic complexity times sigma square by epsilon square. Even if that is not true, the main question that we are interested in is to understand how much does higher order information help in the stochastic optimization setting. We fully resolve this question in our work. We show that access to second order information in the stochastic setting improves over the rate of the first order optimization. But to our surprise, higher order information beyond the second order does not provide any additional benefit for finding stationary points. This suggests what we call an elbow phenomena at p equal to 2 and implies that the conjecture that the stochastic complexity is equal to deterministic complexity times sigma square by epsilon square is not true. Specifically, we provide an algorithm that finds an epsilon stationary point in at most 1 by epsilon cube stochastic gradient and Hessian vector product queries. Note that our algorithm uses a second order or Hessian information through Hessian vector products only, which in many problem settings of interest, for example in deep neural networks, can be computed as efficiently as computing a stochastic gradient. On the lower bound side, we show that in the stochastic setting, no algorithm can beat the 1 by epsilon cube rate attained by second order methods, even when they are allowed to query higher order derivatives. This suggests a stark contrast between the stochastic and the deterministic optimization setting. In the deterministic or noiseless case, access to higher order information strictly improves the rate, but this is not true in the stochastic case. In addition to these results, we also resolve the complexity of finding epsilon gamma second order stationary point in our work. Previously, such rates were obtained under the two-point query model. In this model, the optimization algorithm can query at 2 points simultaneously and get a stochastic gradient at each of them for the same draw of the random variable z. This is, of course, not the case in the fully stochastic setting that we operate in. However, the key idea in this works is to reduce the variance by estimating the difference of gradients. Specifically, given the gradient at a point x, one can compute the gradient at some other point y by estimating the difference of the gradients between the 2 points. These works estimate this difference by an empirical average, which is feasible under the two-point query model. However, these methods require additional assumption on the mean square smoothness of the return gradient estimates. We also use the idea of variance reduction to get our improved rates in the fully stochastic setting. Specifically, we observe that the Taylor expansion implies that the difference in gradients at 2 points x and y is equal to path integral of the Hessian vector products. Our key insight is that this can be approximated by an empirical average of the estimates. This approximation introduces some error, but choosing the number of points to average adaptively, depending on the square of the distance between the 2 points, ensures that the expected error is small. Thus, using this idea of Hessian vector product-based gradient estimator with SGD, we get a rate of 1 by epsilon cube. This algorithm uses first order and Hessian vector product operations only, both of which are computationally feasible for many practical problems of interest. However, needs the gradient to be Lipschitz. We also provide a cubic regularization-based algorithm that uses the full power of second order information and achieves a rate of 1 by epsilon cube without requiring gradient Lipschitzness. At this point, I would take a moment to compare our stochastic second order query assumption with the prior work. Specifically, the mean square smoothness assumption used in the prior work with two-point query access implies stochastic Hessian vector product access. That is, one can simulate a stochastic Hessian vector product using access to a two-point query model. However, the reverse is not true. That is, stochastic Hessian vector product access does not imply two-point query access. Hence, our assumptions are strictly weaker than those in the prior work. Moving beyond the task of finding epsilon first order stationary points, we also consider the problem of finding epsilon gamma second order stationary point. That is, to find a point x hat such that the gradient of the objective at that point is smaller than epsilon and at the same time the curvature is not too negative. That is, the curvature is larger than minus gamma. On the upper bound side, we provide an algorithm that finds an epsilon gamma second order stationary point in 1 by epsilon cube plus 1 by gamma, 5 plus 1 by epsilon squared gamma squared number of stochastic gradient and Hessian vector products. On the lower bound side, we show that no algorithm can find such a second order stationary point at a rate better than 1 by gamma cube plus 1 by epsilon cube queries, even when given access to higher order information. For p is equal to 2, we provide an improved lower bound that matches the leading term in our upper bound. This resolves the second order complexity for finding second order stationary point. Our lower bound requires new techniques and are based on the idea of stochastic zero chains introduced by Arjevani et al. In 2019. These techniques also imply new and tight lower bounds for the deterministic or noiseless setting. To summarize, we provide a tight characterization of the complexity of finding stationary points in stochastic non-convex optimization. We demonstrate that access to second order information improves over the first order rate. However, access to higher order information beyond the second order does not have any additional benefits. This is in contrast to the deterministic setting, where access to higher order information strictly helps. In addition to this, we also mostly resolve the complexity of finding epsilon gamma second order stationary points. Moving forward, we are interested to explore whether these trends are an artifact of considering worst case rates or are also realized in natural problem settings. And we're curious to find if under some mild additional assumptions that consist of natural problem setting, one can in fact benefit from access to higher order information. We are excited to explore this question for future research. Thanks.